Okay, so we're now finishing off security, where we're looking at our final aspect, which is quantum cryptography. So basically, we're looking at this. Focus on purpose, benefits, and drawbacks. So what's the purpose of quantum cryptography? Well, it's used for secure communication. And its idea is to make sure that data sent between two parties, so that's two people, cannot be eavesdropped on. That is its purpose. Secure communication to ensure that data cannot be eavesdropped on between two parties. So how does it work? Now, obviously you saw in the syllabus it didn't say you need to know how it works, but it's useful for you to understand. Well, we've got Alice who's the sender, we've got Bob who's the receiver. Alice starts by preparing a bunch of quantum particles, like photons, which are particles of light. These particles can exist in different states. So these particles which, or photons which Alice puts together are going to be sent to Bob. So they're going to be sent to Bob, so these bad boys here, by using a really secure communication channel. So we call that a secure quantum channel. These particles can be multiple states at once. You don't really need to know that in too much detail. What you do need to know is that what happens is when these photons are sent and they get to Bob, what Bob will do is he will measure the particles. He will tell Alice about how he did the measuring, but not the results. Alice will then tell Bob if the way Bob measured these particles was correct or wrong. If an eavesdropper decides to intercept and trying to listen in on what's going on or look at the data, some of the photons will change, unbeknown to Eve. So when Bob does his measuring of what's being received, and he says it how he did it, and Alice is going to say, yep, you've measured it correctly, that's a right method, these are the results, and Bob is going to be like, I didn't get that as my result. They're going to know that someone has actually eavesdropped on the conversation. So Alice and Bob would basically be able to see that it's been disturbed. That's really it in a nutshell at a really high level, or should I say a really abstract level. These photons are sent to Bob. Bob measures the photons. He then tells Alice how he's done the measuring. Alice will then basically say, yep, you've measured it correctly, or no, you haven't. Then what happens is that these photons get converted into zeros and ones, which creates a key. If Eve is going to eavesdrop, some of these photons will change state. Bob and Alice will both know this because they have their original measurement. The measurement will change. Imagine the measurement was like counting how many blue ones there were. This is going to be different to this, so we know that something's happened. So why would people use quantum cryptography as a model? What benefits does it have? Well, it relies on laws of quantum mechanics. So unlike normal cryptography, it doesn't use or rely upon mathematical problems to solve the cryptography. So if I wanted to crack a password, you'd be using math. So it doesn't care about how difficult, so difficulty irrelevant. So you can make the most strongest password ever, but it can still be hacked. That's basically what I'm saying. So difficulty, not an issue. So that'll be our first benefit. That's what it relies upon. Our second benefit is eavesdropping detection. So basically, for using this, by using quantum cryptography, it ensures that eavesdropping can be detected. This is because of the measuring which is done. Quantum states will change. So when we do the measuring, so we can actually see, okay, one of our photons has changed. So the measurement we get is different, so someone has actually listened to our conversation. We've also got another benefit, forward secrecy. So our current conversation remains secure, even if our future communication gets compromised somehow. So anything we've done historically is kept secure. So imagine I crack into getting someone's WhatsApp, I'll be able to see their history. In this situation, even if someone's to get somehow compromising our communication, anything we've done previously, they won't be able to see. And it offers long-term security. It would take a quantum computer to potentially, we could say, break quantum cryptography. That's going to be very, very rare for someone to have a quantum computer in today's day and age, or in the near future even. So it's making it practically impossible. But what about the cons, the negatives? Well, it's high cost. It's complex. So for example, you need specialist hardware. Especially to do things like lower temperature, which it needs for the hardware. Limited distance. So it needs things like repeaters to boost it on again and again and again. It could get lost on fiber optic cables. And in terms of scalability, it's not straightforward because it's not common, so you can't really expand it. And because of that, it's limited in use. Because a lot of it is still under development. For example, we're trying to do it using digital signatures, but we're not there yet. We haven't been able to do it yet. So, benefits and cons, quantum cryptography, prevent eavesdropping, to have secure communication. And there you go.